Hello, this is the video walkthrough of the Astro 2024 paper for AQA. I'm going to write it there so we know. Some of my students have done this, so I'm going to talk about what they've done. If you are not one of my students and you're watching it, welcome to. But obviously some parts might not make as much sense, or some bits might not be as relevant because I'm going to talk about their mistakes, but they're common mistakes that you might have made as well. So question one, we're going to start off with a question that's generally about telescopes. So a student uses a refracting telescope in normal adjustment to make observations of Jupiter. The telescope has an angular magnification of 75. Now, a refracting telescope is one with two lenses, and the lenses would be in this combination like so. And if this was the telescope and there was the eye, this would be your eyepiece lens and this would be your objective lens. And if the telescope is working properly, we should find that the rays of light would travel through it like this. And if it's in normal adjustment, what we can say is that the distance between the eyepiece and the objective lens will equal F0 plus FE. I'm just going to say straight away now, because I've realised everyone's going to see them, apologies for the state of my nails. It's a long story about having fake nails for too long and now they've been a bit screwed over. So we need to work out what F0 and FE are, and we can do that because we've been given one of them. This 22 millimeters is FE, and on the formula sheet you are given the equation M magnification equals FO over FE. So we're going to rearrange that. FE equals FO divided by M. So 22 millimeters divided by 75. And that comes out as, no, sorry, I've done that completely wrong. That's annoying, isn't the first paper? I'm just copying what I did before, and I made the same mistake before because I've written it out so I can go through it quickly. FE will equal M times F0 even. Wow, we're really doing really badly. I want to know the objective lens. FO will equal M times FE, which is 22 millimeters times 75. And that is equal to 1,650 millimeters, which is equal to 1.65 meters. But that is not your final answer, as I made the mistake of doing. I did this paper and got an awful lot of silly mistakes because I was trying to rush through it. So remember, we need to add these two together to get the distance between the two. So it's going to be 1.65 meters plus 22 millimeters. And that comes out as 1.672 meters, but I'm going to round. There we go. I'm going to round to 3 sig fig there, because that feels about right. 2 or 3 sig fig were allowed in the mark scheme. So then the next question has another little trick in there. When viewed through the telescope, the image of Jupiter subtends an angle of 1.7 times 10 to the minus 2 radians. Calculate in kilometres the distance between the Earth and Jupiter, and they've given you the mean radius of Jupiter. So we are here on Earth, we are looking at Jupiter, and we're told the radius of Jupiter, which is half of the size of it, remember, and the radius is 7 times 10 to the 4 kilometres, which means the diameter, which is all of it, would be 14 times 10 to the 4 kilometres. And we are going to work out by looking at the angle it subtends in the sky, which is this, what this distance here is. Now, don't do what I did, made every mistake in the book on this question and just assumed this is my angle, because this is the image of Jupiter. We need to work out what Jupiter actually subtends, and there's another formula in your formula sheet that looks like this. It's not written exactly the same way, it's written in a more long-winded way, but that magnification is equal to the angular size with the telescope divided by the angular size unaided, so without a telescope. So we know that 75, the magnification, equals 1.7 times 10 to the minus 2 radians divided by the angle we're actually looking for. And that means that the angle we're looking for is 1.7 times 10 to the minus 2 divided by 75, which comes out as, let me just move my answers so I can see them a bit better, 2.66 times 10 to the minus 4 radians, which is quite a lot smaller. Makes sense though, because that's the whole point of a telescope. So this angle here is 2.66 times 10 to the minus 4. And then we can do a variety of things. So you can use either tan or sine or neither here. We can assume or approximate this to be a right angled triangle. And then we can say that this is the hypotenuse and this is the adjacent, or that this is the adjacent and this is the hypotenuse, doesn't really matter. And we can use tan theta equals op over adj, or sine theta equals op over adj. Not op over adj, I'm doing really bad these days, op over hypot, Sokotoa. But the adjacent and the hypotenuse are both d. And for both of them, op is the diameter, so 14 times 10 to the 4, or 14 times 10 to the 4. So we can use either one. We can also, because this is a really small angle, the small angle approximation is that tan theta is approximately sine theta is approximately theta. And if you do these calculations, you'll see they're all coming out about the same, because you can see those two sums are the same. So we can just say that theta equals 2.66 times 10 to the minus 4, which is equal to 14 times 10 to the 4 divided by d, which means d is 14 times 10 to the 4 divided by 2.66 times 10 to the minus 4. Or you might have done sine of that and make sure your calculator is in radians, or tan of that, you get the same answer. And it should come out as 617.6 times 10 to the 6. And remember, this is in kilometres here. So your answer here is in kilometres. There's no conversion needed. I would then generally write that as so 6.18 times 10 to the 8, or 6.2 times 10 to the 8 kilometres. So be careful there. Quite a few things that can go wrong that I definitely had going wrong. So moving on to the next part of the question. The student places a cap over the end of one end of the telescope. It has a circular hole in the centre. The figure below shows it. State and explain the effect that the addition of the cap has on the chromatic aberration caused by the lens. Step 1 here, this is a 3-mark question. Tell me what chromatic aberration is, which I did not do in my answer. So if I was to draw a lens and I was to draw 2 different colours of light coming out of said lens, which I can't do because I've only got a blue pen. I'm highly prepared today, as we can see. I thought I was being clever doing this at home one evening, but clearly not. Oh no, there it is. I've got a red pen. So if I've got light coming into my telescope, I'm going to draw my usual 5 rays. And this is blue light. It's going to do something like this. If it's a telescope, right, it's going to all bend to meet at the same point, except it doesn't do that because different light of different wavelengths refracts different amounts. Blue refracts more than red. So what you'll find is if you've got white light, the red light won't refract as well, especially at the edges where more refraction is happening. The lens is more curved at the edge, so more refraction happens, and we find that there's not this nice clear focus. So chromatic aberration is when light of different colours is dispersed. I've missed an S out there. As it passes through the lens, especially at the edges. Meaning the light doesn't all focus in one place, which is the focal point. Doesn't all focus at the focal point. Now this circular cap, what I've done with the circular cap is I've essentially blocked off this light, the worst light. So the cap reduces, my class got this pretty right, actually decided that it reduces chromatic aberration. And you have to say why. By covering the more curved parts of the lens, or making sure most of the light that's travelling in is parallel or nearly parallel. I mean, it's all parallel here, but it bends less there because it's going into the lens. So that's 3 marks. So you get 1 mark for saying, what does chromatic aberration mean? You get 1 mark for saying it reduces the aberration and 1 mark for saying why. Then explain 2 other effects. There are 2 and only 2. What we have done, well, there's probably more than that, but there's 2 that we have to care about. What we've done here is we have taken the diameter of the lens, and now we've reduced the diameter of the, not the lens, but of the aperture, as in the gap that light can go through, by adding this cap on. So we've reduced D. Now, if we think about when is the diameter of the telescope, of the aperture, important, well, there's 2 relationships. The first, you're not given on the formula sheet, you have to remember for yourself. Collecting power is proportional to D squared. So reducing D reduces collecting power. And you have to tell me that relationship to get the mark. And then you have to say, therefore, what does that mean? It means the image is dimmer or less bright. It's getting less light. So collecting power is about brightness. The other thing that it affects is the Rayleigh criterion. Now, the Rayleigh criterion is this. Theta is approximately lambda over D. Decreasing D increases the Rayleigh criterion. Remember, the Rayleigh criterion is the smallest thing that can be resolved, really. So increasing that means you've got a lower resolution. And so reduces resolution. It doesn't seem to like, though, you just saying that. You have to say what that means. It reduces resolution. And that means the image is less clear. Now, I originally wrote less detailed, and I think that is fine, but it's not in the mark scheme. Less clear. I also think blurrier would be fine, because that's what less clear means, but there we are. So you get a mark for each of those relationships, and then a mark for saying it's going to be dimmer and it's going to be less clear. Okay, so that's question 1. We'll move on to question 2, which is all about parallax. Now, this is another one where you don't get all the formulas involved. So the apparent change in position of a nearby star relative to distant stars is due to an effect known as parallax. Angle A is the parallax angle. This can be used to determine the distance to a nearby star, provided that the relative motion between the star and the sun is negligible between observations. They've given you the distance from the sun to S is 79 light years. And then they've said that the Earth takes 6 months to move from P to Q. So what that means is that this is the Earth's position in, let's say, January. This is the Earth's position in, let's say, June, the first and 6 months. And the Earth is going to orbit around the sun, which is here, which I'm not going to call S because S is also that there. So here's the sun. Now we know by definition that this distance from the Earth to the sun is 1 AU, as is this. So this whole side has got a side of 2 AU. I'm going to split this by drawing that like that, and then I'm going to label this angle here P, because they've said that A is the parallax angle, but actually we generally go for this being parallax angle. And then this is the equation you need to remember. D equals 1 over P. D is distance to star, but that has to be in parsecs. And then P is the parallax angle, but that is in arc seconds. So we're going to use this equation, but step 1 is I need to convert this 79 light years to parsecs. So it's 79 light years, but each 3.26 light years is 1 parsec. So I'm going to divide by that, and I get 24.233 parsecs. So now I'm going to put that into this formula. P equals 1 over D. I've just flipped those around. Equals 1 over 24.233. And I get that my parallax angle is 0.041266. Now, that's in arc seconds. I need this in degrees. So I need to convert that, and I do that by dividing it by 60 twice. There are 60 in terms of angles, 1 degree is 60 arc minutes, and it's equal to 60 times 60, 3,600 arc seconds. So if I divide that by 3,600, I get this in degrees, which comes out as 1.146 times 10 to the minus 5 degrees. But we've not finished yet, because that was this. A is double that. So A equals 2 times 1.146 times 10 to the minus 5 degrees. And that's another thing I forgot to do. I did loads of them wrong. And that comes out as 2.3 times 10 to the minus 5. So you have to have known this equation, including the units, to be able to do that question. So then on to part B. Parallax is used to determine the distance to a different star. Observations of the star produce the following data. Distance determined using parallax is 0.4 pc. Apparent magnitude is 13.5, absolute magnitude is 16.7. And astronomers suggest that the star moves significantly relative to the sun between the two parallax observations. Discuss whether the suggestion is valid. Now, this is another one where I think the mark scheme is actually quite mean, but having marked it, what I think we need to pick up on is this bit here. It says, this can be used to determine the distance provided that the relative motion is negligible. And they're asking us here to say, is it negligible? i.e., is this actually how far away that star is? Or is it not negligible and we can't use that calculation? What we have been given that we can use though is the apparent magnitude, little m, and the absolute magnitude, big M, of that star. So what we're going to do is use the equation you are given, which helps you compare these. So little m minus big M equals 5 log d over 10, and we're going to do that to work out the distance. Now you can do it this way, or you can use the distance and m to find the other m. There's loads of different ways. Look at the mark scheme for it, but I'm going to go for this version. So then I'm going to write that m minus n, m even little m is 13.5 minus 16.7, it should be a negative number there, divided by 5 equals log d over 10. And that means that d over 10 is going to equal 0.299. I did the calculation. 0.229, sorry. So if you do this term and then you 10 to it, so 0.229 is equal to 10 to the, no, I've not written it down there, 13.5 minus 16.7 divided by 5. That's how we kind of switch to the log. So that means that D is 10 times 0.229, it's 2.29 parsecs. Now, that is very different to this. So to get 3 marks, 1 mark is to use this and get 2 of the numbers in it right. 1 mark is to get this distance right, or to get another m right up there. And the 3rd mark is to say 2.29 is bigger than 0.40 parsecs. So not valid. The 4th mark, it's quite vague. It basically, I think it kind of says you need to go into a bit more detail. Why could it not be valid, or why is it not valid? Well, you could say, because this is a significant difference. And we can see how significant it is by comparing those 2 numbers. So you could do 2.29 divided by 0.4. It's about 6 times bigger, which is a lot. So that would be one way to do it. I think another thing to think about is we know that the closest star to us, Proxima Centauri, is about 4 light years away, which is about 1 parsec away. So it seems odd to have a star that's 0.4 parsecs away, because that's even closer. Another thing that rings alarm bells here, but this is still possible, it's really normal for your absolute magnitude to be smaller than your apparent magnitude, because they usually be brighter. Absolute magnitude, remember, is the brightness you'd be at 10 parsecs away. So that means that this must be less than 10 parsecs away, which it's not impossible, but rings some alarm bells here. So maybe mentioning something like that, I think, is quite useful there. But not the easiest of questions to get all 4 marks for. If I marked your paper, I wrote 1, 2, 3, 4. 1 was for this, using that equation. 2 was for getting a correct number. 3 was for this comparison. And I don't know if anyone got 4, but it was for that extra bit of information. Okay, moving on to question 3, a bit more about stars now. Now, in this version of the paper, it's really easy to miss the first part of the question. In the real paper, how it's printed, it'd be much easier. But the figure below shows a variation of intensity with wavelength for a star. Show that the above figure is consistent with a black body temperature of about 6 times 10 to the 3 Kelvin. Now, straight away in my head, I think, Wien's law, lambda max times T equals, let's write it down somewhere, 2.9 times 10 to the minus 3 Kelvin, not millikelvins, it's meters Kelvin. So I basically need to prove that this is right. And I'm going to find what temperature this graph would give me. So if I get a ruler, which surprise, surprise, I'm at home, I don't have with me, and I draw a straight line going down like so, you should get that this lambda max is about 0.48 micrometers. 0.47 is fine. Okay, so I'm going to say that temperature equals lambda divided by 2.9 times 10 to the minus 3, which is 0.48 times 10 to the minus 6 for micro, divided by 2.9 times 10 to the minus 3. And that gives you a temperature of 6,042 Kelvin, which is pretty close to 6,000 Kelvin. Therefore, yes, it agrees, and you have to say that, or it's consistent. So it's a pretty simple question if you saw it. Then another pretty simple question, these ones often are. The radius of the star is 9.6 times 10 to the 6 meters. Calculate the power output. This is Stefan's law, sigma times A times T to the 4 equals the power output. But a really important thing here is this is the area, it's the surface area of the star, which is a sphere. And the equation for that is 4 pi r squared, not pi r squared, not 4 over 3 pi r cubed, nothing else. Also make sure that you to the 4 your temperature. So P equals sigma, which is 5.67 times 10 to the minus 8, times the area, 4 pi r squared, so 4 pi, and then 9.6 times 10 to the 6 squared, times temperature, either 6,000 or 6,041, but you need to do that to the 4. And then that comes out as 8.5102, but if I'm writing it to, let's write it to 2 sig figs because that's what everything else is written to. 8.5 times 10 to the 22 watts. Lots of people that I marked got that wrong because you either did a circle, not a sphere, or didn't do to the 4 or something like that. So just be careful there because that's an easy question. C is deceptive. Which row gives the type and spectral class of the star? Now 6,000 is between 2 spectral classes. It's between G and F. It's like the borderline between the two of them. So we have to work out, it could be this one, this one, this one, this one. Most people, myself included originally, just think there's G, it's that. I didn't even see there's another G underneath. I didn't even look at the types of star. So we have to think about, is this a white dwarf, but a bit cooler? No, not cooler, sorry. A white dwarf or a main sequence or a red giant. And the way we're going to do that is we're going to think about its radius and its power output. This is a pretty high temperature, a pretty high power output. What you could do is, you know, an example of a G-class star, you could do P equals sigma A T to the 4 for the sun. You know that this is about 5,700 Kelvin, I think it is. The area pi 4 pi r squared, that's on your formula sheet. And you could actually figure out the power of the sun as a comparison, and you'd find that this is much bigger. So this is a much bigger power than, well, it could be a red giant, I suppose, but I think it would have to be a red supergiant, and the temperature's too high for a red giant. So it's going to be a white dwarf. So the answer there is this one, F, because it's got such a high power and it's actually quite a small radius. That's how we're deciding that, but really hard question there, so I'd understand if you didn't get that one. We then move on to the light from the star, which passes through an interstellar dust cloud before reaching Earth. The reduction in intensity when the light passes through the cloud is assumed to be inversely proportional to the wavelength of light. An astronomer on the Earth estimates the blackbody temperature of the star. Discuss the effect that the dust cloud has on this estimate. Now, there's a few ways you can get this slightly wrong. The reduction intensity is assumed to be inversely proportional to the wavelength of the light. That means longer wavelengths are absorbed more. Hang on. The reduction in intensity is inversely proportional to the wavelength of the light. Nope. Longer wavelengths are absorbed less because they will have a smaller reduction intensity. Shorter wavelengths, and I've done the question before, are absorbed more. Now this means the lambda peak that you measure will be longer than in reality. Because a lot of the shorter wavelengths, you're going to kind of cut off some of your graph, like here, some of it's not going to get absorbed as much, so it won't look as if it's as peaky, as it were. So the peak that you measure will be longer than it should be, and then lambda max times t equals a constant. So if this is longer than it should be, then if this stays constant, t should be lower. So therefore, the temperature estimate will be too low. Now, lots of people have done what I did originally, which was this. I wrote a little formula, change in intensity is proportional to 1 over lambda, and I thought, well, that's going down, so this is going up, which is a more simplistic way to think about, but is not right. The idea is that it means that shorter wavelengths are absorbed more, therefore just won't appear on the graph as much, but longer wavelengths will appear on the graph, which means that the peak that you measure will be slightly wrong. So if you got 1 mark for that off me, you probably did similar to what I did. 1 mark was for saying the temperature will be too low, but that was contingent on getting something right here. So I did allow that 2nd mark if you'd said something like this, but you couldn't just say it's too low and guess. You had to give a reason why, and this reason was the 2nd mark. Right, final question. The Earth is in the galaxy known as the Milky Way. The Andromeda Galaxy is one of the closest galaxies to the Milky Way. It's approaching the Milky Way at a speed of 110 kilometers per second. The distance between the galaxies is 770 kiloparsecs. Discuss whether the data can be used to estimate an age for the universe. Now, lots of my students here tried to do things, and most people only got 1 mark, but it's a really simple question, this. First things first, be really, really specific. What do we use to estimate an age for the universe? So we use 1 over h naught to estimate the age of the universe, universe's age, found through V equals h naught d, or Hubble's law. And V equals h naught d, this is a recession velocity. Andromeda is approaching us, not receding. It's blue shifted, so it can't be used. And your 2 marks are here for saying no, it can't be used, and why. You have to say something about the fact that we're using Hubble's law to estimate the universe's age, but you have to say why. You can't just say no because it's moving towards us. No, it's moving towards us, and we use Hubble's law, i.e. things moving away from us, to work that out. Part B is a really easy way to get 3 marks. I managed to miss a mark out from just doing a really stupid calculation error. There's a supermassive black hole at the centre of Andromeda Galaxy. The mass is 1.6 times 10 to the 8 solar masses. Calculate the radius of the event horizon. All we're doing here is using the Schwarzschild radius equation. R equals 2gm over c squared. So using our formula sheet, g is 6.67 times 10 to the minus 11. From gravitational fields. M, 1.6 times 10 to the 8 solar masses. So you have to multiply that in, and a solar mass from your formula sheet is 1.99 times 10 to the 30. So do all of that and then divide it by 3 times 10 to the 8 squared, don't forget, and you should get a nice easy sum here, 0.978 23596. I'm going to just round that to 3.6 times 10 to the 3 unit. It's a radius, meters. Don't make it harder than you have to. You can put it in AU and all different things, but just keep it in meters, make your life easier for yourself. And then finally, our 6-mark question, or a longer question, it's kind of a bit of a gift. I think the mark scheme's a little bit like weird, what they want you to say, but it's basically just asking you to talk about quasars. So what is a quasar? What is the point of a quasar? Well, not really what's the point of a quasar, but what does it tell us? Go on to suggest why a quasar might be produced as galaxies merge, and in your answer you should describe properties, observations that they provide evidence for those properties, and suggest the process of quasar formation and why it's likely when 2 galaxies merge. So a quasar is a quasar is a quasi-stellar object. You don't really get a mark for that. I'm going to do a little bit of note form because you can do that if you are careful. They have a very large power output, i.e. they're very bright, and generally they have very large redshifts, which means they're very distant from us, and that also means they're very old, although you don't get a mark for saying they're very old. And what that tells me is if they're very large redshifts, very distant, very old, is what we're seeing is we see them in early galaxies, because when we look further back, if we look 12 billion light years away, we're looking back 12 billion years in time, and we're seeing galaxies as they were long ago. Closer galaxies, as in ones that we can see more in their more recent history, don't have quasars. They only seem to be in early galaxies. Now what we think they are is we think they are the energy or radiation that is produced when stars at the center of a galaxy, and it's a young galaxy, fall into the supermassive, you have to say this, you can't just say black hole, the supermassive black hole at the galaxy center. I've not written the word hole. At the galaxy center. So we think they only happen at the start of a galaxy, because when all the matter in the Schwarzschild radius has been, I'm going to say consumed rather than eaten, by the supermassive black hole. Please write that out fully. The quasar stops. Now, what does this mean? Well, if 2 galaxies merge, the supermassive black holes may become active again as new stars fall into the Schwarzschild radius, which will mean the quasars also start up again. Now, when it comes to the mark scheme here, you have 3 areas. You have the properties, you have the observations or the evidence, and you have the formation. And I think the easiest thing to talk about here is the formation, but we'll go through each of this and I'll label if it's a property or not. So, or which bits they are. So properties, if it's associated with a supermassive black hole, that's a property mark. So saying it's associated with a supermassive black hole is a property mark. So is saying it has a large power output. That's a property mark as well. Saying that they're distant is a property mark, and that they're small compared to the galaxy. It says treat any comment about age as neutral, which I think is odd, but there we are. Evidence is that they have very large redshift. That's evidence that they're distant, right? Because that's how we work that out. Evidence is that we see them in the centre of galaxies. That's why we think they are from the supermassive black holes from the past, because that's where they would be. Saying a large redshift is all I've already talked about one, haven't I? You can say that it's a bright source, especially if you say it's a radio source, because they would have not given out radio waves originally. It would have been like much more high energy radiation, like X-rays, gamma, but they have redshifted to radio over time. And you can also say that there are rapid fluctuations in power output. Everything else here is really how they form. So it's when material moves towards the centre of the supermassive black hole. So a lot of this here is the formation. And then all of this one is how it could form again. Now, to get 6 marks, you have to cover all 3 areas. So you'd have to have marks from each of those areas. It says at least 2 are covered in some detail. I would argue that I've covered F in quite a lot of detail, and I've given a pretty decent version of the other 2 parts as well. So I would give this 6, but you can get errors. You can have 6 marks even if you've got an error or you've missed a little bit out. So it's quite a generous mark scheme for that. But that is the end of the astrophysics paper, because that's the last question. It's only out of 35. In terms of this paper and its grade boundaries, I do not have them all written down helpfully, but I can tell you that an A star out of 35 is 24. An A is 22, so a very small difference there. And a B is 17. And then below that, I can't remember off by heart. But there we go. You can see I do think that astrophysics is a lot more predictable and a bit more straightforward and a place to get the marks on those papers. But hopefully that was useful, even with some of my garbling, especially in conjunction with the mark scheme. Any questions? If you know me, just ask. If you don't know me, soz, you'll have to cope without.